So now we're going to look at combining the laws that we have learned so far. So we talked about Boyle's law, which relates pressure to volume. We talked about Charles' law, which relates volume to the temperature in Kelvin. And we talked about Gay-Lussac's law, which relates volume to the number of moles. And in each case, we have to keep two things constant. We have to keep, in this case, in the case of Boyle's law, we have to keep the temperature and number of moles constant. In the case of Charles' law, we have to keep the number of moles and the pressure constant. And in the case of Gay-Lussac's law, we have to keep the temperature and pressure constant. So the question now becomes, what happens if all these variable changes? Then we end up with a combination of these laws, which can be represented by this expression right here. V is directly proportional to NT divided by P, or PV over NT is equal to a constant, or we can express it this way, which again is convenient in terms of solving for one item if we know what the others are. All right? So this basically, if you look at this equation closely, you'll see that it's very related to all of these. For example, in the case of Boyle's law, the temperature and the number of moles will be constant. So that means that N1 will be equal to N2 and T1 will be equal to T2. So if these two cancels out, if let me get to my pen here. If this part cancels out with this part here, we'll be left with P1 V1 is equal to P2 V2, which would be essentially Boyle's law. All right? So that shows you the versatility of expressing the different laws combined in this way. All right? So let's move on to the next slide, which is another example. It says, the flask pictured in this figure contains oxygen, the one to the left at STP and the one at the right at 100 degrees Celsius. What is the pressure at 100 degrees Celsius? So basically, what we have here is, well, we can use this equation, P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Now, it's the same flask, so therefore the volume remains the same. So therefore V1 and V2 would be equal to each other. We can cancel those out. And we're assuming that the amount of gas is fixed. So therefore there's no change in the amount of gas that is present in the flask, which means that N1 would be equal to N2. So therefore we can cancel out those. So therefore this equation will be reduced to P1 over T1 is equal to P2 over T2. And what the question is asking for is P2. So to find P2, we can rearrange this to get P2 is equal to P1 T2 over T1. And all we have to do from here is plug the numbers in. So in the case of, hold on 1 minute. Okay, what's going on with this here? So in the case of P1, that would be 1.00 atmospheres because that's standard pressure. T2 is 100 degrees Celsius, which would be 273 Kelvin. I'm sorry, 373 Kelvin. And T1 would be 0 degrees Celsius, which would be 273 Kelvin. And then we do the calculation here. So 1 times 373 divided by 273. So according to my calculation, this works out to be equal to, when rounded off to 3 sig figs, this would be equal to 1.37 atmospheres, because the Kelvin units will cancel out here and here. All right? Okay, so that's basically how this problem will be solved. All right, now, oh, there's another question here which is blocked out by my writing. So let me erase this to see what this is saying. Okay, so the question is asking, what pressure would be exerted if the vessel were transferred to an oil bath at 200 degrees? Well, we use the same equation. The only difference now is that well, let me write the equation here. It's P2 is equal to P1 T2 over T1. So the initial pressure would be the same, which is 1.00 atmospheres. But now T2 is going to be 200 degrees, which would be 473 Kelvin. All right, divided by the initial temperature, which is 273 Kelvin. So let's see what that gives. So that's 473 divided by 273. Okay, so according to my calculation, this works out to be equal to 1.73 atmospheres. Okay, so that's basically how that is done. Okay, so now we're going to get into a law which combines all the laws that we discussed, right? Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. And this is basically a summary of these laws right here listed. So basically, as we said before, Boyle's law is, well, one way of expressing it is PV is equal to a constant, but that's if N and T are constant. In the case of Charles' law, that would be volume divided by temperature is equal to a constant. In other words, well, and the number of moles and pressure is constant. Pressure divided by temperature is equal to a constant. That's Gay-Lussac's law. And in that case, the number of moles and volume is constant. And then finally, volume divided by the number of moles is equal to a constant. That's Avogadro's law. In that case, pressure and temperature must be constant. So if we combine all these laws together, we're going to get PV over NT is equal to a constant K. And that constant is given a special designation and name. It's called the molar gas constant. And it turns out that the molar gas constant has a value of 0.08206 liters atmospheres per mole Kelvin, right? And it is very often rearranged in this way. In most textbooks, you'll see that they actually express it this way. PV is equal to nRT, and that is called the ideal gas equation or the ideal gas law, right? And a couple of things you need to be aware of when it comes to using this equation. The pressure is in atmospheres, the volume is in liters, the number of moles is, of course, moles, and T is in Kelvin. So when these are the units, then this would be the value of R, and please note the units associated with R here. In fact, associated with this value of R, right? So if the value of R is 0.08206, then the units associated with it would be liters atmospheres divided by mole Kelvin. Now, if you're going to use other units for these variables, then you're going to end up with a different value of R along with a different combination of units. And that is shown here in this slide. So this is the R that we were talking about before, and that is true when the pressure is in atmospheres, when the temperature is in Kelvin, and the volume is in liters, and the mole unit is included. Now, if the pressure is in torr, then that changes the value of R to what you see here, all right? And you'll notice the unit changes because where you have atmospheres here, that is changed to torr here, all right? Now, if the pressure is in pascals and the volume is in meters cubed, then that changes the value of R to this right here. And please note that when that happens, then the units of R becomes joules per mole Kelvin, right? So the point here is that the value of R that is used in the ideal gas equation is dependent on the values or the units that different variables are expressed in, right? So it all depends on, you know, the type of problem or question that you're given. Now, let me just say that in the vast majority of cases in this chapter, you'll be using this value of R, all right? But later on, when we get to a discussion of, I think it's Graham's law, what you'll find is that this value of R will become important, all right? So when we get to that, then you'll see why this value of R is used in that situation. Okay, so I'm going to stop here, and then we're going to look at some examples of questions involving the use of the ideal gas equation, all right? Until next time.